4.5, the dimension of a vector space. Dimension's a pretty friendly idea. Let me jump right to the definition. Dimension is just the number of vectors and a basis for that vector space. Simple as that. Once you have your basis, count the vectors, you've got your dimension. So let's run through a few examples of what we're looking at. So I have a vector space or a subspace. What do we see here? It's a set of vectors in R3. I see 3 entries. So we have this strange structure to it. All we know is there's some scaling of some stuff going on. I know S and T are some real numbers, so let's break this down. What we can also see here is if we were to unpack this, again, it looks like we've got S is scaling 1, 4, 0, and T is scaling -3, 1, -1. So here's another way to see this. We have a basis of 2 vectors, 1, 4, 0, -3, 1, -1. And that's where we stopped in the last section. We were looking for a basis for a subspace. Well, we're just going to extend it by one more idea. The dimension is 2. We have 2 vectors that pull this off. So again, to help think what this is, we've got a set of vectors in R3, and there's only 2 of them, and so what that tells me is we've got a plane through the origin in R3. Doesn't cover all of R3. There's some vectors we can't get, but we've got these 2, dimension 2. Second example. Find the dimension of the subspace of R2 that's spanned by these 3 vectors. Well, if we just stare at these for a little bit, it won't take you long to realize that starting with this first one, this second one is just a scaled version of this by -3. And the third one is a scaled version of the first, scaled by -1. So what we really have here is a basis. All we need is one of them. And if I just pick this guy, and if we're just looking for the dimension, it looks like it's 1. So the basis for this subspace is this first vector. I don't need these 2 guys. They're just scaled versions. So my dimension is 1. So what do we have here in R2? It looks like we have a line through the origin in this direction. Third example. Let's see. All right. Okay. Find the dimension of the subspace of R3 that's spanned by these 4 column vectors. Well, so let's just notice a few things. Yes, these column vectors are in R3. We have 4 of them, so we've got lots to play around with here. Is it possible they cover all of R3? Well, maybe. One thing that's not clear is I don't see any direct scaled versions of vectors here. It was close on this first one. It looks like the first one just got scaled by 2 to get the second, but it's not quite. We've got a sign issue going on here. And so I don't see any direct scaling going on, but it doesn't mean there's not a linear combination that's hidden behind the scenes. So what we're going to do is our classic, well, let's reveal what's going on here. And let's do this. If I were to take that matrix, and I just want to double check in my calculator, we've got this going right, we're good. If I were to scale this, or I'm sorry, row reduce it, it ends up being this guy. So what does that tell me? What wasn't obvious before is now obvious. I see 3 pivot columns. This last one turns out to be just a linear combination of the first three, and so it looks like we can cover all of our three, but all I would need would be the first three columns. So with all that, if I were to ask for the basis for this subspace, you could just use the first three columns. But if the question is what's the dimension is 3, because I have 3 pivot columns. All right, fourth example. I've got a matrix, and we're not going to row reduce. I just want to stare at this thing and see if we can figure out a few things here and then make some general observation. So I've got it looks like we're definitely it's an echelon form. It's not row reduced because I don't have zeros above, but this is all I need. I notice the question is, how many pivot columns do you see? And I see clearly here, this guy, eventually we would divide through by -3, but we don't need it, and this guy. So there are 3 pivot columns, and that pretty much reveals the column space. Or I'm sorry, the dimension of the column space. Well, the null space is going to be built on the other 2 columns. Remember, if we were to call out all 5 variables, I would have 2 that would be free variables, and then my null space would be defined based on those 2 variables. So that reveals the dimension of my null space. And in general, you can say the dimension of a column space of any matrix is just the number of pivots in that matrix, where the dimension of the null space would be the number of free variables. And that's a pretty nice generalization we have. Once you put in an echelon or even row reduced, once you can identify pivots and free variables, you've got your dimensions. All right, last couple of things. It turns out R3 has some pretty identifiable subspaces, and it might surprise you, there's actually 4 unique subspaces in R3, and we can start to classify them by their dimension. So let's start with if I just something obvious. Let's say you've got a dimension of 1 in R3. What does that tell me? Well, that means there's 1 vector inside R3 that's taking care of this subspace. So imagine you're being asked to span a single vector in R3. And so what is that? It's just a line through the origin. So any line through the origin has dimension 1. So let's bump it up. Dimension 2 means there's 2 vectors that form the basis. Let's see, that's a 1 and that's a comma. And so what is that? Is a plane through the origin. So those are the 2 probably classic ones that we can visualize, a line and a plane in R3. But what if I took it all the way and we said the dimension 3? Well, there are 3 vectors then, x1, x2, x3, that form a basis. And what is that? It's just all of R3. Well, I said there's 4, and the one I skipped over was actually I should have started with, but I wanted to end with, what would a dimension of 0 be? And it turns out it's just the 0 vector. Remember, all subspaces have to contain the 0 vector, and if that's all it has, that's it. And so what is that? It's just the origin. No dimension. All right. So the final one I want you to think about, bit of a challenge here. Think of the standard basis for I've got 3 of them here, so let's just do them one at a time. The standard basis for Rn. So the standard basis again, we're talking about the cleanest basis you could come up with, like 1001 for R2. So if you had a standard basis for any R space, what would its dimension be? I'll come back to that. We've talked about polynomials. So P sub n. Again, this is all polynomials of certain degree or less. What would the standard basis, if you had the standard basis for a polynomial vector space? Predict its dimension. And we've also talked about matrices as vectors. So a generic matrix M by N, if you had the standard basis for that vector space, what would its dimension be? All right, I want you to hit pause or think for a moment, and here comes the answers. N plus 1, M times N.